Good evening, everyone. Can you hear me? Good evening, everyone. Can you hear me? So today we are going to discuss the parallel resonance. In the parallel circuit, you have both R, L, and C are in parallel, and it is driven by a current source. So as you know that in resonance, or you can say at resonance, total reactance, or you can say imaginary part of Z, or you can say total susceptance, that is the in case of we are taking the admittance, that is the total susceptance must be 0. So instead of finding the Z here, you should find the Y. So Y is equal to 1 upon R plus 1 upon J omega L plus J omega C. This is your Y. So 1 upon rearrange little bit, 1 upon R J omega C minus 1 upon omega L, and this at for resonance your total susceptance, that is reciprocal of reactance is susceptance. Total susceptance equal to 0, which means omega C minus 1 upon omega L equal to 0, which gives you the omega n, that is the resonance frequency, is equal to 1 upon L's root over. Clear? So this is the at resonance the Y will be the at resonance your Y is equal to 1 upon R, which is maximum or minimum, because Y as the before resonance Y is equal to 1 upon R. Some other terms, when you take the magnitude, it will be definitely greater than 1, so it will be minimum, and your G will be the, if Y is minimum, G equal to R, that is maximum, that is impedance is maximum. Okay, and what is the V? See here, this V equal to I upon Y, that is I into R, and power P max, that will be at resonance maximum power, P max equal to V square upon, because this is the V, so current through the resistor is the I, current through the resistors, that is your IR, is equal to V upon R, that is I, and P max equal to P max is equal to I square, IR square into R. This is the P max at resonance. Okay, so let us draw the functions with respect to omega. Here is your omega n, this is your 1 upon R, which is equal to conductance, right? And because your y is equal to 1 upon r plus j omega c minus 1 upon omega l, right? You can say that minus 1 upon, if it is 0, so minus 1 upon omega l, when omega 0 it is infinity, like that it will come, and omega c is a straight line. So at omega n, okay, I did actually a little bit of so at omega n, this point, because omega c and 1 upon omega l are equal. Okay, now we can go. Okay, and at this point you have g, that is 1 upon r. So you can easily write that y, magnitude of y is like this, and you can easily say that at omega n, both voltage and current are in phase. At omega n, both voltage and current, that is at resonance, both voltage and current are in phase. That at omega n, okay, please join if you think that you have learned these things. Some extra things you may encounter, right? And there are some inherent tricks, so that you can easily remember for the long term, right? So this is the at omega n, both v and I are in phase at omega n. Okay, and between 0 to omega n, which one dominates? This is your 1 upon omega l, and this is your omega c. That means y is inductive or capacitive? Y is capacitive, because you see here, this is your y. When this term dominate, that means this is greater than this, so it's a negative. I have told you, when the negative sign, it will be a capacitive. So y is capacitive, that is admittance is capacitive. So obviously your impedance is 1 upon y, that is it will be inductive. This is the you can say analysis, you can say reasoning you do in the exam hall. You cannot remember all these things at a single go. Understand this. Okay, inductive. If z is inductive, obviously I lags v, and once it is, and beyond this omega n, similarly y is inductive, and your z is capacitive, and your I leads V. Clear? And if you compare it with the series circuit, this is just reverse. At this point, both V and I are in phase, and you will see that here Z will be capacitive. Z will be capacitive, and I leads, and for series, and here Z will be inductive, I lags. See the duality applied here. Okay, now we'll tabulate voltage, a value of voltage and current at in general. For reference, I will draw the circuit once again. This is your I, this is your V, this is your R, this is your L, and this is your C, this is your IL, because V is constant, and I, C, and IR. Clear? So in general, at resonance, in general, you have V equal to I upon Y, that is I upon 1 upon R plus J, then omega C minus 1 upon omega L, and at resonance your V equal to I R, and which is equal to I into R, that is maximum. Because at that case your Z is maximum, so Z equal to R, that is maximum, so V will be the maximum, right? And you see that there in the series RLC circuit I was maximum. This is the duality. Here V will be maximum, there I was maximum. Then we have IR, which is the V upon R, and what is the V? This is the I into R, 1 upon R plus J omega C omega L, and here that will be the IR will be the simply this is 0, RR cancel, so I, and which is again maximum, all the currents, and your IL V upon J omega L, so I upon J omega L into 1 upon R plus J omega C minus 1 upon omega L. This is a general term, and at resonance your IL will be, this term will be 0, so that will be the minus J R upon J omega, sorry, not J already gone to the top, R upon omega L, and obviously I is there, so you can write this is minus J I Q P, that is quality factor of series, quality factor of parallel circuit, right? So this is the, then next is the IC, so quality factor of the parallel circuit, which is R upon omega N L. Okay, so that is V upon 1 upon J omega C, which is J omega C upon I 1 upon R J omega C minus 1 upon omega L, right? And at resonance your I of C will be the J omega C R into I. J, this is not negative, should be confusing. J omega C R I, that is J I QP. What is the QP? QP is the quality factor of the parallel resonance circuit, which is omega n R C or R upon omega n L. Quality factor, same definitions. Maximum energy, maximum power, reactive power in inductor or capacitor upon the maximum true power. You will find these relations. So you can easily see that. Okay, you see here at resonance, your IL plus IC equal to 0 and the magnitude is amplified by it can be amplified, it cannot be amplified, because if QP is less than 1, then it may not be amplified. That is not always true that it will be amplified by. Sometimes Q can be less than 1. This Q quality factor, okay, is quality factor cannot be negative, so greater than 0. So it can be like 0.1, it can be 0.01, it can be 10. Okay, so if you 0.01, it will be you can see it is less than that is less than the supply current. Okay, so now calculate half power frequency. Half power frequency, same relations. Maximum power we have seen, P max is equal to I square R. So P half is the I square R by 2, right? And we have seen the, in general, V equal to what? V equal to I upon Y, that is I upon 1 upon R plus J omega C minus 1 upon omega L, right? So you know this is the V. You have a resistance R. So what is the relations you have studied? That is P will be the V magnitude square upon R. So this is your resistors. So I magnitude square, or I already we have taken the I magnitude with I square, or I magnitude you can take. We are assuming that 0 phase for the supply current. So for when the supply phase has a 0 phase, then I magnitude square is same as the I square. This is the square, so 1 upon R square plus J omega C minus 1 upon omega L square. Okay, V magnitude square into 1 upon R, which is equated to the half power frequency, and frequency at which that is your power is half, that is I magnitude square R by 2. I magnitude cancel. You can easily compare it here. That is, this condition R by 2 will be, you see here 1 by R square, right? And here into 1 by R. If this term becomes 1 by R square, these terms, what happens? So 2 into 1 by R square. So 1 or 1 cancel. So R upon 2, that will be, that means omega C minus 1 upon omega L square should be 1 upon R. This is the condition for the half power frequency. We will simplify a little bit here to find the actual value. That means omega C minus 1 upon omega L magnitude, which is equal to magnitude is equal to 1 upon R square. Yeah. equal to 1 upon R. So this is the condition for the half power frequency. That is, half power frequency occurs in a parallel AC circuit in a parallel RLC circuit half power frequency occurs half power condition occurs when magnitude of total susceptance, this is susceptance, it's not reactance, okay, total susceptance, magnitude of, when magnitude of total susceptance is equal to 1 upon R, that is conductance. Okay, this is the condition for the half power frequency in parallel RLC circuit. So omega C minus 1 upon omega L is equal to plus minus 1 upon R. By solving this, you will find same that time in the parallel in the series circuit we have found out. So you will find omega 1 is equal to, that is, this is the curve, this is the omega n, this is the omega, and this is omega 2, and this is your upper frequency, that is 1 upon root 2, magnitude is 1 upon root 2, this is 1, okay, and this is the that is relative magnitude, okay, and this is omega 1. So omega 1 is equal to, I have told you, sigma minus sigma square plus sigma square plus omega n square root over, and omega 2 will be the sigma square and plus sigma square plus omega n square root over sigma. For parallel RLC circuit, sigma is equal to, for series it was what is the sigma, R upon 2L. So use the duality, you can easily get it. In place of R you replace the G, in place of L you replace the C, that is 1 upon 2 RC, okay, and omega n as usual 1 upon LC root over. Clear? So let us find out the critical conductance, like we did the critical resistance for the series RLC circuit. Here we are going to find the, and also damping ratio, right? Any issue in the live stream? Can anyone say? All fine in the live stream? Okay, there is fine. This is your system domain. I will be coming to find the critical conductance. So this is the Ls and this is the 1 upon Cs, right? So Y is equal to 1 upon R plus 1 upon Ls plus Cs. So V equal to I upon Y. Okay, fine, there is I upon Y, that is I upon 1 upon R plus Ls plus Cs. So you can see here RLS into I, RLS into I, then RLCS square plus R plus Ls. So take out common RLC. So 1 upon C I into S upon S square, then 1 upon RC into S plus 1 upon LC. Okay. So characteristic equation becomes equation becomes S square plus 1 upon RCS plus 1 upon LC equal to 0. And and so discriminant is the b square minus 4ca. This is the x square bs plus c. So discriminant d is equal to d is equal to b square minus 4ca, that is 1 upon rc square minus 4 upon lc root over. How to find the G critical? G critical at which your discriminant d equal to 0. Discriminant d equal to 0. That means 1 upon rc square is equal to 4 lc. Now in place of 1 upon r, you replace the G critical. G critical square upon C square is equal to 4 upon LC, which implies G critical square for C upon L. So G critical is equal to 2 CL upon root over, right? But this is the series. For parallel, we calculated R critical. So by seeing this, I can write L by C. Duality. Dual of R is equal to G. Is a const. 2 is a constant. Dual of L equal to C. Dual of C equal to L. Okay. Now come to the find the what we'll find. We'll find that is your zeta, damping ratio, or damping constant. damping factor will be damping ratio, which is equal to actual G upon G critical, right? Actual G upon G critical is by definition. Okay, G critical. What is the G here for the parallel circuit? That is 1 upon R and 2 root over C upon L. So now put these values. So this is the 1 upon 2R L by C root over. This is the zeta for the parallel circuit. But we found the zeta for the series circuit. Zeta for series circuit, if you look at this, you put 1 upon 2 in place of R, put the G because duality. In place of L is a C, in place of C equal to L, that is R by 2 into C upon L. Okay, R by 2 into C upon L. So with this duality you can easily find out the zeta. Anything left? Left. Sigma already we have discussed. Yeah, sigma attenuation constant. So attenuation constant, that is 1 upon 2RC. Okay, now we'll go to the tank circuit. Okay, all rest all are you will be finding out. You will be like bandwidth of the parallel circuit. That day I have tabulated it. Bandwidth of parallel circuit is equal to, see here, same relations, omega 2 minus omega n, that is 2 sigma square. Sigma square, oh sorry, not square here, nobody is pointed out. This is sigma, 2 sigma, so 2 to 1 upon RC. So bandwidth will be your the 1 upon RC, and Q is the 1 upon 2 zeta, and F1 F2 all rest all are same. Okay, so there is no difference. So it's better when you make your note, right? Just draw a comparative table so that you can remember only one and you can do the all others. Okay, for example, when you making note, write down here the series important relations. Let's say series resonance, parallel resonance. For example, just I am giving an example. Let's say R critical. What was the R critical for the series RLC circuit? That is 2 root over L by C, right? Yeah. So use the duality. So R critical means it will be G critical. R duality of R is G constant root over C upon L. Zeta, what are the zeta? R by 2 C upon L. And for using the duality, zeta is a ratio. Okay, zeta is a ratio, so duality same. That means zeta means this is a 2 ratio. So this is the not separate. Zeta is valid for both the circuit, and this is the G. You can write 1 upon R, and C for L, and L for C. Then omega n 1 upon L C, omega n 1 upon, for L you write C for L, so remains same. Okay, when you make the notes, you can do in this fashion, so that if you remember one thing, then automatically you will be recollecting the other one. Let us move to the tank circuit. This is your RL, series resistance of a practical inductor. Okay, this is the L, and this is your RC. Okay, one series, the loss is represented by RC and the C, right? And driven by a current source or voltage source, not an issue. So let us find the Y. So if this circuit will be at resonance, that means your Y, that is the imaginary part of the Y must be 0. So Y is equal to 1 upon R L plus J omega L plus 1 upon R C plus 1 upon J omega C. Okay. So this will be the RL minus J omega L upon RL square plus omega square L square. Clear? Plus RC minus J omega C upon the J, this will be plus. Okay. This is the RC square plus 1 upon omega square C square. Right? So when you do the cross multiplications, that is you simplify it, RL square plus omega square L square into RC square plus 1 upon omega square C square, then your RL minus J omega L into RC square plus omega square C square plus this, that is the RC plus J upon omega C. RC means the series resistance of the value of the capacitors into RL square plus omega square C L square. Okay, so you can take out the this will be the imaginary part. This part will be the imaginary part. You can easily see that omega L minus omega L RC square this, and this will be equal to 0. That means all this 0. So I can write simply omega minus omega L R C square plus omega square C square plus 1 upon omega C into R L square plus omega square L square equal to 0. This is the imaginary part will be 0. Imaginary part of the Y will be 0. Okay. You can easily see that little bit of cross multiplication, take out the negative terms to this side. Then you do the little bit of calculation here. Okay. Then ultimately you will get in this fashions, that is your omega n, because imaginary part will be 0. So after simplification, this you will get the 1 upon LC root 2 over, okay, and RL square minus L by C upon RC square minus L by C. Okay. Now the question arises, if you do this calculation, it will take time. So how to remember this? Many of you may be mugging of these things. See that it is very easy. Okay. Let's say B blank. Okay, now we are blank. We know that omega n is equal to, for any circuit, it is 1 upon series or parallel 1 upon LC. We have studied. Okay, now the terms will be a ratio. Okay, the terms will be a ratio of two things. At least you have the idea. Okay, that is, you have RL for the and L inductor, and you have RC. Okay, then you have for the capacitors. So, but you know that L upon C root over is a resistance. Unit will be resistance. L upon C root over will be a resistance. Okay, so you can write here. So L upon C is a resistance, then L upon C root over is a resistance. So L upon C will be the resistance square. So obviously there will be, because we are taking the root over, because this L upon C taken outside, root over of L and C taken outside, obviously this ratio will be some root over. So root over RL square minus, because this is a ohm square, so you need to write L upon C, because L upon C is the resistance square, that is the ohm square, the unit. Then RC square minus L upon C. Whole things will be in the this. Just think when both the RL and RC equal to 0. Both the RL and RC, that is the resistance of the series resistance of inductor and series resistance RC equal to 0. That means you expect this. It is clearly happening. When RC equal to 0, RL equal to 0, L upon C equal to 1, and you get the 1 upon LC. Right? So this is this relations you need to only remember with all the intuition I have given you. So I will write once again L upon C root over, and one confusion may come. One confusion I want to also remove that confusion. Sometimes when you are in exam hall, you may be thinking whether it is RC square, whether it will be RC square upon L by C root over upon RL square minus L by C root L by C. This may be also, even though you remember all the things, but this confusion may give you the wrong answer. Okay, how to eliminate this confusion? This confusion is simply eliminated by this relations. This relation L upon C is the ohm square. That is, in the numerator is L and denominator C. So here the RC comes from the capacitors, so in the denominator, and RL comes from the inductor, it is in the numerator. Okay, so this analogy can remove the confusion between the RC and RL, which term will be in the numerator and denominators. Okay. So we need to consider two important case. Okay, case 1. Case 1, when RC equal to RL. It is rare case. Okay, still we need to mathematically it can be possible. So omega n, because this become 1, so omega n equal to L by C. What will be the impedance? Impedance at resonance. How to find the impedance at resonance? Just put omega n you got. This term is 0. Imaginary terms will be, all the imaginary terms will be 0, and omega square, in place of omega square you put the 1 upon LC. Ultimately you will get the Z, impedance at resonance is a resistive, so that Z will be the R by 2, because R and RC equal to RL equal to R, so R by 2 plus L upon RC into 2. See, this is the only you have done in the plus 2 course, that is the dimensional analysis. Anything you need to, it should be dimensionally valid, any relation should be dimensionally valid. So you see the Z is the ohm, so R by 2, here L by C equal to ohm square and upon R ohm, so ohm, that means dimensionally valid, so you can easily, if you don't forget, if you forget you can easily remember. Case 2, normally this thing, this is the case we normally go for it, that is we assume, that was the general case. Case 1 is the RC is rarely happens, but as capacitor drop is the very less than the, that is your RC is very less than the series resistance of inductor, we can safely assume that RC equal to 0 and RL equal to R. That means your resonance circuit, that is the tank circuit, is like this. R, L and C. So obviously omega n will be the 1 upon LC root over, just put that RC equal to 0 and RL equal to R. So you will have 1, let's calculate. So RL square minus 1 upon LC upon RC is 0, so minus LC. So 1 upon LC root over of 1 upon H, that is 1 minus C upon L RL square, C upon R square, that is the R square, this is the omega n. And impedance, for this case impedance at resonance, Z will be the famous relations. What is that? LC upon R, LC R at resonance. This is this is the famous relations. Everywhere it is used in the tank circuit. That is, impedance at resonance for a tank circuit of this nature is the L upon CR. Okay. So how to, sometimes you may not remember. Suppose by any way you write the like this, C upon LR. So C upon LR is the 1 upon ohm square into ohm square, so ohm Q. So relation invalid. So if you know the transmission line also, it can be reducible. L upon C is equal to ohm, the unit is ohm square, upon ohm is the ohm, so that this is the purely real. Obviously that is real at resonance, na? Okay. So let us move to some of the question recently asked in the GATE exam. There are a lot of questions from the resonance, but we will discuss the some of the questions so that you can have an idea the type of question it is coming in the actual GATE exam. The figure shown, can everyone see? Okay. The figure shows a RLC circuit with a sinusoidal current source, right? A sinusoidal current source. So at resonance, the ratio IL upon IR. You know that at resonance, so see here, very simple one. The ratio of the magnitude of the inductor current phasor to the resistor current phasor. At resonance, this current, you know already. Current, maximum current flows through the R, that is your IM. So your IR is equal to IM. Magnitude, that is the amplitude. The ratio of the magnitude of inductor current phasor. So IM upon root 2. This is the phasor for the resistors, and for inductor IL, which is equal to minus J Im upon root 2 into Q. So when you take the magnitude of the both the phasor, that is IL magnitude ratio of IR magnitude, so you have root to root cancel, Im cancel, so you have only what is that, Q, Q, and Q of parallel resonance circuit, just now we have discussed, that is L upon R upon omega L or omega RC. So R omega is the your 1 upon LC root over into L. Okay. So R C upon L root over. So R is the 10 ohm, root over of C, that is C is equal to 10 microfarad, is 10 to the power minus 5, and L equal to 10 millifarad, 10 to the power minus 2. 10 into 10 upon 10 root over of 1 upon 1000, right? So 1 upon root 10 root over. So which comes out to be how much? 0.316. 0. All correct. A little bit of question and little bit of tricks. This was the question asked. Yeah, it is in the GATE question of EC 2017 or 16. This is the this year question in the instrumentation. In the circuit shown, omega equal to 100 pi radian per second. R1 R2 equal to 2.2. L equal to 7 millihenry. The capacitance C for which Y in is purely real is in millifarad, rounded up to 2 decimal place. People will think that, see, that's why I have, see, first of all, people will see that R1 and R2 here. When they see that, if they write that R, then they will think that okay, this is equal and this it can be done easily. But see the question, they have also R1 R2 equal to 2.2 ohm, that they are equal. They are equal, right? The condition case 1. Case 1, RC equal to RL, so omega n equal to 1 upon LC. See, exactly from this relation they have asked one question for you. Okay, so it turns to be a trivial one. Yes or no? Even though you don't remember case 1, case 2, just write the omega n is equal to 1 upon LC root over. Why I am writing omega n? Because it says that yn is the purely real. What do you mean by purely real? Purely real means the circuit is in resonance. Okay, circuit is in resonance. That means this frequency omega is your resonance frequency, and equating with you can get the result. Given that R1 R2 equal, so omega n reduced to be 1 upon LC, and equate omega n is the 100 pi. So 1 upon LC is equal to 10 to the square. Take the square of the both side into pi square. So C equal to 1 upon L into 10 to the power 4 into pi square. And what is the value of L? They have been given 7 into 10 to the power minus 3 into 10 to the power 4 into pi square, that is 1 upon 70 into pi square. Use the calculator for this little calculation. You will get the 1.447 millifarad. Right? So easy. So easy. Don't go by the picture. The picture may be frightening or fearful to you, but the result is a simple one. This is the aptitude question actually. This type of question are aptitude. GATE never asks the long calculation questions. Okay. So this is the aptitude question, only can be done through practice a lot of questions and understanding concepts very deeply. Okay, and that can be achieved. How you will understand very deeply, and how you practice a lot with dedication and devotions, and only you sleep, study, eat, study. Wherever you are, whatever you do, you should think about your study. And if you are feeling that you are not study today or not study for 2 hours, if you are feeling guilty, that means your success is near. Understand this. Whenever you are attending some birthday party and you think that I am wasting 2 hours because of this birthday party, I could not study, and you are repenting that, then you are in the verge of success, because you will not repeat again, because a wise man does not repeat his mistake. A wise man does not repeat his mistakes. Okay, very clear, very easily you can do. Okay, this question we can do now, later on. Okay, these are the two questions I have selected. So before going to end the class, I will be taking some that is your coupling, that is a magnetically coupled circuit, right? Let's discuss for 10 minutes. Magnetically coupled circuit. You might have seen that whenever a transformer is C, there is a dot. Dot can be here, dot can be here. This type of can be possible, or here is a dot. Sometimes here is the dot. What does the dot indicates? In a simple word, your teacher might have told you, when you connect a positive potential here and varying it, then it will be reflected positive. This terminal will be positive and varied like this. Or if you are increasing the current in this terminal, the current will be increasing out of this dotted terminal. Similarly, the dot. So how it is possible in a circuit? How the dot comes? How can you determine the dot? Dot can be simply determined by the Lenz's law. Lenz's law. The famous law is the Lenz's law. Okay. Now see here, when the for example this cycle is going increasing, so flux will be by using your right hand rule when the finger calls along the direction of the current increasing. Okay, current is current. So you can see that the path of the flux is this, right? Path of the flux is the this. Now tell me which terminal will be have a in potential positive when this potential is positive and increasing, which of the terminal will have here positive and which terminal will be negative. So use the Lenz's law. What does Lenz's law say? That the induced voltage in the linking coil will be with the give induced voltage will have the in the linking coil will have the polarity in such a orientation when connected a load. When you connect a load, it will produce a current through the coil which will oppose the very cause it producing it. Very cause producing, that is the cause is the this one. When you connect a load here, it will produce a current in such a direction, it will oppose this flux. This is the causing flux. It says that obviously opposed flux will be the this one to the coil, this one. Lenz's law says that whenever a uh, the causing for current is or voltage is increasing and it is linking flux is linking and producing a flux phi, it is linking to the other coil. The coil will have a potential in orientation in such a way that when the load is connected, the current will flows. The current will flows which will produce a flux in a opposite directions. The meaning of it will oppose the flux, the very cause which producing it. Very cause is the this phi and it should be opposed. So to oppose this, and we have a induced flux, okay, or opposing flux, I say phi naught, which will oppose the causing flux phi. So what should be the current flowing if I connect a load between this terminal? The obviously same, use the right hand rule. So obviously the current direction should be this, as it has to upwards. That means this terminal will be positive, this will be negative. In a similar fashion, you can calculate for this coil, let's say coil 1, coil 2 and coil 3. This, so the current direction will be the simply, what will be the current direction? This one. That means this will be positive and this negative, right? That means you will have the induced flux, induced volt potential will produce when the load is connected in the induced coil, it will produce a current which will oppose the and produce a induced flux which will be producing opposing the causing flux. So this is the when this is the dotted here, we mark the dot. So for this coil, dot will be here. For this coil, dot will be here. So normally we can replace like this. This is dot. For this coil, dot is here, and for this coil, dot is here. Coil 1, 2. Hope it is clear. Same way, when you have, this is the magnetical coupled. So when you have the inductor, linked inductor, so they are coupling. So whenever dot here and let's say dot here. So how to write the equation for this? And you apply a voltage, and this is the current I. This is the L, this is the L, and they have a mutual inductance M, right? So here very simple is, you know, when they are not linking, using the KVL. Same way you will write the KVL. See here, first of all, when the current flows through the dotted terminal, this terminal will be positive, this terminal will be negative. Similarly, when current flows through the undotted terminal, so when undotted terminal is the positive, so undotted terminal will be positive in this linking coil. So you simply write like this, you traverse in direction. So you first encounter L2 di upon dt. Now see the, due to the, this is the for the self inductance. Now you encountered a dot. Now current flow in this dotted terminal, so this will be a positive. So you are going from the negative to positive. So it is the M di upon dt. Similarly, now this coil is over. Similarly, you can write for this coil L1 di upon dt plus M di upon dt, which is equal to V, which is equal to L1 plus L2 plus 2M di upon dt, right? So if you compare it with a single inductance, inductance, it is the L equivalent, which is L1 plus L2 plus 2M. In similar fashion, you can also do for the dot here and dot here. See here, what? So you can instead of you can remove this dot and 1 second, you can remove this dot and you can represent with an equivalent circuit like this. L1 is source of a source of M di upon dt, then L2 a source of M di upon dt equal to V, and this is your I. Remove the dot and replace with the equivalent circuit. Same way, see that I am writing the opposing case. Series adding. Earlier was called the series adding, and this will be called series opposing. See the dot here, dot here. Now the magic will happen. How it will become? Now I traverse in these directions. So L2 no issue, L2 di upon dt. Here. Now come to the dot case. Now see here, the current entering in the dotted terminal, right? So dotted, according to Lenz's law, dotted terminal positive. That means the source will be like this, plus minus. You are traversing from positive to negative. So negative M di upon dt. Now for this is the curve positive. So L1 di upon dt. Now come to the case, because current through the L2 producing a voltage at L1, but current entering in the undotted terminal, I is entering in the undotted terminal in the L2. So undotted terminal will be positive, dotted terminal will be negative, and you are traversing from positive to negative, so a negative sign M di equal to V. So this becomes V equal to L1 plus L2 minus 2M di upon dt. Clear? Now come to the, suppose you have this is a parallel. Suppose you have a series L1, L2 series opposing. V and this is the I. So for this case, if you write this type of terms, it will be a very huge equation. Instead of doing that, you just convert into the and equivalent to another inductor like this, L equivalent, right? Same V and I. So here you have to only do one thing. This is converted to Laplace L2S, and this linking is the MS. Okay, I'll write again. Okay, VI. Now this is your I1, I2. So write V KVL, V equal to L1 is I1, right? Clear? Now see here, because the current through L2, okay, current through L2 produce a induced voltage in L1. So, but current in L2 enters in the undotted terminal. So, here undotted terminal will be positive and dotted terminal negative. So, it will be minus MS I2, right? But you know I equal to I1 plus I2, right? This is the equation 1, because here three variable are there, because we need to relate between the V and I. Now second equation you can write in this loop, which is L2 is I2, okay, L2 is I2, then it is entering dotted terminal, so this will be the positive, this will be positive, this will be negative, so minus M is I1, then it come to the minus because you are traversing this way through this, so I1 is entering here, so this is a positive negative, so minus L1 is I1. Now you see, because here is a dot, but okay, a dot, so you need to see where the current is entering in the L2. It is undotted terminal, so here the undotted terminal will be positive, okay, that is plus MSI2 equal to 0, okay. So we got L2S plus MS I2 is equal to MS I1 plus L1 is I1. Okay, let's say SS cancel. So L2 plus M into I2 is equal to M plus L1 I1. Okay. Now come to the, we have three equation now. So we can easily eliminate this I1, I2. Okay. Okay. V upon, a second, let me check. Otherwise, to do this, it can be a simpler one. Otherwise, it will be increasing to a bigger one also. L1M. Okay, let's eliminate this first. So we'll do one thing, that is the I1 I2. Yes. What we'll do? see here, L2 plus M I, okay, we'll do M plus L1 into I1 is minus L2 plus M I2 equal to 0, and another equation is the I1 plus I2 equal to I, right? So you know how to solve this type of equation. For example, if you multiply L2 plus M in the both the side, like L2 plus M I1 plus L2 plus M I2 is equal to L2 plus M into I. So this and this cancel na? Okay, this and this cancel. So you have, see here, L1 plus L2 plus 2M into I1 is equal to L2 plus M into I. So I1 is equal to L2 plus M upon L1 plus L2 plus 2M into I. In a similar fashion, you will calculate the I2. For I2, what you will do, you will multiply M into L1. M into L1 in the both the side. M into L1. So, and with a negative sign. L into M1, and when you subtract, okay, L into M1 when you subtract, you will have same. That is your 1 second. So you have M L1 plus M upon L1 plus L2 plus 2M into I. Now put these values here. So V is equal to L1, S common gone, L1, and I1 is the L2 plus M upon, let's say L simply P लिख लीजिए इस टर्म को, L1 plus L2 plus 2M is a P, then minus M into L1 plus M upon P and I. So I into S P upon L1 L2 L1 L2 L1 plus M minus L1 plus M cancel, L1 L2 minus M square, L1 L2, yeah, minus M square. That means your V is equal to L1 L2 minus M square upon L1 plus L2 plus 2M into S into I. That means this is a L equivalent, which is L1 L2 minus M square upon L1 plus L2 plus 2M. है ना? हाँ. So that's why they directly don't come in the exam, because it is taking a lot of time. That time you must click this, otherwise you will be in a otherwise you will be in a infinity loop. You will put this one, this one. If you, this has to be strike in your mind first, that is this equation and this equation, both the variable of I1 I2, and you need to find the I1 and I2. Okay, so let us move to that questions. This question that was asked in the GATE 2023 this year. It has the a sinusoidal current I1t is equal to 1 sin 200 pi t milliampere. is flowing through 4 Henry inductor, which is mutually coupled to another 5 Henry inductor carrying I2. This current I1 and I2 as shown in the figure. The coupling coefficient between the inductor is 0.6. The peak energy stored in the circuit in Joule. So coupling factor there, so you can find the mutual inductance M equal to coupling factor K L1 L2 root over. Once you find the M, so peak energy stored in this magnetically coupled circuit is the energy stored in the first coil, half L1 I1 square is a peak value, okay, IM1, IP1, that is a peak value. Whenever you are taking half, because it is a, so peak value is a 2 here, peak value is the 1, so that's why we are divided half. Then second coil, half L2 IP2 square. Then third is the M L1 M, that is M one coil, linking coil, I1 IP1 IP, this is the, and putting these values, M calculate from here, putting this value you will get the some 17 point something. How much it is? Yeah, 17.36 microjoule. These are straightforward that is a formula based questions, and which is again appeared in the instrumentation branch. So we find that for the instrumentation branch it is very much important, that is your coupling circuit also, as well as your resonance circuit, because many people are appearing in the dual papers also, so that you can equip for the that. And for the electrical it is always understood, coupling is their basic, coupled circuit is their bread and butter, I can say, for the electrical engineer. If they don't couple anything, you will not have motor, you will not have generator. Okay, with this we end the class for the day, and if possible we will plan the tomorrow for the class. Okay, see you in the next class.